The part that I work for is based in London, and it's called London Connected Learning Centre. At London Connected Learning Centre, we have a range of technology and technological expertise, and we sort of share that with the schools around us that are close to us. So we do in-school workshops and staff training for teachers. We also, sometimes we welcome teachers and their classes to come to our centre to do workshops. And we do all sorts of different things with technology, sometimes using technology to teach many different subjects, but also specialising in computing and computer science. So recently, it was in 2014, England introduced a computing curriculum which includes programming activities. And so basically every child from the age of 5, every child in England has to learn the fundamentals of programming. And that has had a really big impact on our schools, as you can imagine, because most teachers who teach 5-year-olds don't really know very much about programming. So they've had to learn a huge amount of stuff in a very short amount of time. And so I suppose what I want to talk to you a little bit about today is sort of how that process has gone for our teachers, what kind of things we've learnt from it, and what are some of the really fundamental ideas that you might be able to incorporate into your own teaching to help children to develop these kinds of skills. And you can see, so I've got two quotes to show you before I start. So the first one is, this is from the computing curriculum. It's from the purpose of study, so it sort of outlines why the national curriculum writers think it's important. And it says that a high-quality computing education equips pupils to use computational thinking and creativity to understand and change the world. So everything that we do in teaching children computing has to kind of incorporate these things. And I think that's an important thing to remember, because we're partly helping children to develop what are known as computational thinking skills, kind of like problem-solving skills, a little bit of critical thinking, but we're also inviting them to use their creativity. Because as we all know, children tend to be fascinated by technology. Most children have technology in their lives in some form, but many children, the relationship they have with technology is very much as consumers. They're using technology, but they're not necessarily learning how it works or learning to change it or learning to create their own. So the idea behind teaching children computational thinking skills and teaching them programming is to empower them to become creators and not just consumers of technology. And I had this up a few moments ago. This is a quote that I like from a lady called Jeanette Wing, who's an academic in this area. And she said that computational thinking is a way that humans, not computers, think. And that's a really important thing to remember, because sometimes when someone says computational thinking, you think, okay, we're talking about computers, we're talking about, it must be programming. And yes, if you're writing a program, if you're doing some programming, you will be using that skill. But the computational thinking is something that happens in here. It doesn't happen on the computer. And you can, in many ways, you can teach computational thinking skills without even needing to use a computer. So in this session, we will start with some activities which don't use computers and which you could do just using paper, using pupils' bodies in the classroom. And then we'll move on to some activities where you might do some work on the computers as well to apply those principles in a practical way. So this is kind of a bit of a rundown of what we're going to be doing. Defining what we mean by computational thinking, what the sets of skills and concepts and ideas are that children need to understand to become good computational thinkers. We'll have a little bit of time thinking about what algorithms are and some examples of what an algorithm is, because this is a word, the word algorithm, it features in the computing curriculum for primary school children in the UK, and it's quite a technical term. So when it first arrived, many teachers were a bit terrified. They thought, wow, I don't really know what an algorithm is, and now I'm suddenly supposed to teach it, and it was a bit intimidating for them. But actually, the idea of an algorithm, it's not really that complicated. It's not that confusing. You just need to see some examples that that kind of illustrate what algorithmic thinking really is. And as I said, we're going to do some unplugged activities as well to demonstrate that. So to start off with this question, what is computational thinking? I think it's important for me to say that although I have some answers to this question, I am just one of many, many people in the world, and there are lots of answers to this question. We could define computational thinking in many different ways. So what I'm going to do is provide a way of answering this question that I think is useful, and it breaks it down into some different terms, but I say that with also with the message that there are other answers to that question, and you might find other people who define computational thinking in a slightly different way. But this is what I kind of use as my starting point when I'm thinking about how to teach children to be computational thinkers. This is a poster. It's a resource that was created by this organisation called Barefoot. They're part of so when the English curriculum was introduced, there was this organisation that was set up, which is called Computing at School. And Computing at School, their job was to help to enable teachers to teach this whole new subject. And they set up Barefoot as a place to put unplugged resources, so paper, like lesson plans and ideas, that they can use, so you can find them online and you can print them off and use them with your class. And one of the things that they have is this poster. So what I'm going to do today is talk you through each of these different concepts, which you can see on the left-hand side. But as well as having the kind of the ideas themselves, the knowledge within this subject, to be able to be a computational thinker, you also need to be able to use each of these approaches that you can see on the right-hand side. So as I go through each of those ideas one by one, you'll notice that some of the activities, we're kind of using these approaches as well. We might do a little bit of tinkering, might do some creating, some debugging, some persevering, and maybe some collaborating as well. We might get you to work together a little bit later on. But we're going to use that sort of set of concepts on the left as a structure to guide us through some different ideas for our activities. So, yes, the first thing to say is that the computing curriculum, as I said, is introduced all the way through primary school and then as a new subject in secondary school. In English schools, there used to be a subject called Information Communication Technology, or ICT. And ICT is kind of like what was before computing. And ICT often involves using computers and often making things with computers, a bit of Word, a bit of spreadsheets, that sort of thing. And a lot of schools did really great things with it, but that it didn't have that programming side to it. It didn't have the computer science elements, and it's the computer science elements we're going to think about today. But computational thinking exists in other subjects too. It's not just in computing. So, for example, in early years, in our nurseries, in our reception or kindergarten, we don't actually teach computing as a separate subject. But when children are doing maths and they're learning about numbers and counting, they're developing really valuable skills that will help them to solve problems later in their education when they start to think about programming. There's also an area of the early years framework called Understanding the World, and it's all about just children sort of interacting with the world, and that includes finding out a little bit about technology. As children get a little bit older, once they're age 5 to 7, the curriculum is then a bit more specific about actually what computer science stuff do they need to know at this age. And the answer is not really very much. It's just these three points. They're quite sort of basic ideas. Their language might be sort of initially confusing, but once you get your head around them, it's pretty straightforward. They need to be able to understand algorithms. They need to be able to create and debug simple programs and to use logical reasoning to predict the outcomes of programs. And maybe they might make their own program and predict the outcome, or they might look at somebody else's program and predict the outcome. And actually, it's really similar when they get a little bit older. It's just a little bit more detailed. So this is for age 7 to 11, and at that stage, children they design, write, and debug programs. They can solve problems by decomposing them, and that is something we're going to have a little bit of a go at later on. What exactly that means in programming terms. They have to use sequence, selection, and repetition in their programs. And so sequence being things put into an order and then happening one after another. Selection being where in a program there's more than one outcome depending on what happens. So for example, you might have so if you think of like a thermostat in a room that's taking readings of the temperature all the time, if the temperature goes above a certain amount, then it turns on the air conditioning. That would be a process. That would be a program that had an element of selection in it, because the device is making a choice using the program. And then also repetition, which is just when things happen lots of times. They might keep on going almost indefinitely, or they might happen for a certain number of times. They need to be able to work with variables, variables being numbers that can change, and we'll look at some examples of that later on. And also to have an understanding of inputs and outputs. So if you put one thing in, if you do something, what happens at the end, what comes out. They need to be able to explain simple algorithms, which I think is interesting because it's to do with it's kind of to do with programming and computing and instructions, but it's also it's a verbal skill, or it could be a written skill. It's about communication. So not just being able to copy what the teacher does and kind of follow the same steps, but actually explain and understand why what they're doing works. And that's something that I think a lot of people miss. I think that although teachers they've had the curriculum for 3 years and they're learning and they're getting better in their practices, there have been a lot of challenges that teachers have faced. And I think this is one area that many teachers find it difficult to ensure that their pupils really understand what they're doing and why it works the way that it does when they're programming. And then lastly, detecting and correcting errors, or you might also hear this described as debugging, so finding and fixing problems really in your programming. So to go to the first concept on that list, we're going to have a little bit of a look at some activities that you might do to help children understand the ideas of logic. And so I've designed something, and I've designed it using Scratch. Is anybody familiar with Scratch? A few people. So you may have seen it before, you may be completely unfamiliar. I'm going to assume that you are unfamiliar just because that's fair. And I'll explain a little bit about what it is. So Scratch is a tool, it exists in a web-based form, so you can use Scratch online. But also you can download the software, so you need internet access to use it. In Scratch, you can create these characters. They're called sprites, and every object that you can interact with on this screen is a sprite. So this thing here is a sprite. These buttons, because we can click them, are also sprites. And basically, you give each of those objects its own set of instructions in order to make your program do what you want it to do. Not just with, so it could be, I use it a lot with teaching maths. It's very, very good for teaching maths, but you can use it with lots of other subjects. This particular example, so when children are a little bit older, I'll get them to use Scratch to make, to kind of design projects or to test out mathematical theories or make their own programs, basically. But when they're younger, sometimes I make the program and it helps me to teach something else. So in this particular case, have people seen these guys before? This is a bee-bot. So bee-bots are floor robots, and basically they have these arrows on their back. If you press forward and go, it will go forward, and it will remember the instructions. So if you then press right and go, it will still go forward from last time, and then it will go right, which is why it also has this button called clear, so that if you want to start your program again, you can just give it a tap and then you can put in some new instructions. So I've made a Scratch project that I use sometimes with a class so that I can illustrate this to all of the children at one time before they start using the bee-bots. I'm just going to demonstrate it once it's loaded. There we go. So this is what Scratch looks like. And if you find, always allow. There we go. If you find a Scratch project online and you're interested to know how somebody has made it, you can actually kind of go inside and you can find out how they've made it by clicking on the button up there. And then you can also, in Scratch, you can change the instructions that somebody else has made. So this shows you how I've programmed this project. Now, for young children, I normally use this example project with children aged 5 to 7, so I probably wouldn't go into this much detail about it. But as they get older, they might be curious and they might say, "Oh, Miss, how did you create this project?" So then they can have a little look. But just to demonstrate it, you can put it into sort of a full screen mode like this, and then you can find out what the project does. So at the bottom, as well as those arrow buttons, I've also got this grid with the number on. And if I click on it, you can see it changes the background. Ooh, come on. There we go. It changes the background, and I can set some squares so that I can see where my character's going, or I can put those numbers back. And often I'll say to the children, okay, I'm going to press some buttons now. Can you predict where the Bebop will end up? So let's say I press forward, forward, right, forward, forward.
This is the game, because you give it the direction and the lead and go. I remember it now.
Yeah. So there's lots of other things you can do with it, but yeah, that's right. And there is also an iPad app for the Bebop. You might have seen that before on iPad. So it basically does the same job as this. I mean, maybe I'm biased because I made this, but personally, I think that this is slightly better because it tells you what buttons you've pressed. It shows you your program. When you do it in real life or when you do it on the app, you can't see what your program is, and it can be really confusing for young children to remember a sequence of like 5 instructions and what they're going to do. So I think it's quite helpful to have that information on the screen. So I'll show children this, and I'll say to them, okay, so forward will make it move forward a square, backward will make it move backwards. Left and right, they always cause a little bit of confusion because left and right, they don't actually move the Bebop, they just make it turn. They make it change direction. So usually when I show children this activity, can you guess what they say, where they say the Bebop will finish? If it goes forward, forward, right, forward, forward. So forward, forward, right, forward, forward. Above 5. So that is what children will say. They'll say it will go forward, forward, and then it will move to 12 because it's going right, and then it will keep on going forward. But in fact, if I show you, it goes forward.
33.
Let's see.
33.
13. So it is indeed 13, as you said, and that is because the right arrow makes it change direction. It doesn't actually move the Bebop. It can only move forwards or backwards, which means you're always having to think when you're about to run your program. You have to try and think like the Bebop. You have to visualize which direction is going to be facing in at which time and what's going to happen next. And so by applying that kind of prediction process, you're practicing your logical skills. And that's why I find this activity helpful. I also think that it's helpful for children to go through that process and that kind of debugging process of getting it wrong and then understanding why they've got it wrong. I think it can be really useful for them to go through that process at the beginning together so that they don't feel like nervous or fearful about making mistakes later on. Okay, so that's kind of one example of how you might teach logic to children. But I did say that we were going to have a go at doing something a little bit practical and working together a little bit. What we're going to do now is we're going to work in pairs. I'm going to ask you to get onto your feet, and you're going to become a Bebop. So in your pair, one of you now know how the Bebop works. The Bebop can go forward, it can go backward, it can turn left, or it can turn right. In your pair, I'd like one of you to be the Bebop, and the other person to try to program the Bebop. So the Bebop's job is quite tricky because you've got to remember all their instructions. And if they don't say clear, if they don't press the clear button, you have to try and remember all the other instructions that they've given to you. But if they do press the clear button, then you just start again from scratch and you have another go. So would it be okay if maybe if you guys work together and then maybe if you guys work together and then we've got some pairs on our tables and then we'll just have just a minute or so practicing what that might look like in a primary school classroom with children working together. Okay? Okay, well done, and thank you for being a good sport and having a go, or just for discussing what you've been learning. So you can kind of imagine seeing that activity in a room with adults. You can kind of imagine how it would go with children. Usually it's pretty chaotic. Usually they get a little bit excited. Sometimes they trip up over things a little bit. Sometimes they forget the last set of instructions, but they find it good fun. And I think it's helpful for them to think, to go through that visualization process with their own body and actually act it out for themselves. It makes it much easier for them to understand when they're trying to do it with using the technology. So the next idea we're going to think about is algorithms. And again, so this is something that there are some different schools of thought in how you describe an algorithm and what counts as an algorithm. But in a general sense, an algorithm is it's a set of instructions or rules. And so they have to be a sort of thorough set of instructions or rules. They have to be easy to interpret and understand. And an algorithm, in computing terms, if you make an algorithm, it might be that your algorithm could work in lots of different programming languages. So for example, you might make an algorithm for a quiz game. And it might be a text-based quiz game that you could make in a text-based programming language, or it could be a visual quiz game that you make on something like Scratch. But the algorithm would still be the same because the steps and the instructions are the same. The plan is the same. So I'm going to give you an example of an algorithm, and I want you to execute this algorithm. You should have, maybe not everybody has. People got paper in front of them. So grab yourself a piece of paper. If you need pens, I've got some pens here as well. Need a pen? Oh, thank you. Thanks. And all you need to do is, so I'm thinking of a character, thinking of a monster character, and it has a circle for its body. It has 2 eyes. It's wearing a crown. It has wings, and it's got 4 legs. Your job is simple. Can you draw the character that I am thinking of on your paper? I'll give you about 30 seconds. See what you can come up with. And stop. Okay, so don't worry if you haven't quite finished, but can I ask everybody to just hold up your paper and show me what you got? Interesting. You guys have got quite similar ones. Very nice. Very nice. Like it, like it. Lovely. Okay, so what if I told you that I wanted you to draw a character that looked like this? And I can't see any characters that look like this. They all look a little bit different. Actually, some of them look the same as each other, which is really interesting, but they all look different to mine. And, well, why? Why do they all look different? Well, I guess the reason that they don't look the same and they don't look like mine is because my algorithm wasn't very good. It was pretty rubbish, wasn't it? An algorithm is meant to be a detailed step-by-step set of instructions or a formula for solving a problem or completing a task. So this was supposed to be a list of instructions to help you complete the task of drawing that character. But it wasn't detailed enough. Maybe if I'd given you this diagram with little pictures of each step, that might have helped. Or maybe if I just described things in a little bit more detail and I'd been more specific about where things should be, then that would have helped too. And again, this is an activity that I will do with quite young children, and that it's nice because it's a way of using instructional language, but without them having to be able to write every single step. So they don't need to, they might have a little bit of writing skill, but if they're age 5, actually they can do this without needing to be able to write. If they have a piece of paper or if they have a whiteboard in front of them, they can follow my instructions, and then I say to them, well, now you've all made your own different monsters. Can you make a better algorithm? Can you communicate it to the person next to you and see if you can get them to draw the same thing? So usually this will be followed by an activity where they design their own character and they make their algorithm, but they'll usually communicate it verbally because it would be difficult for them to write down all of those steps. And instructional language is also part of the important part of the English curriculum at that stage in England. So this fits in quite well within a cross-curricular way, as well as being about computational thinking. This is an activity that I borrowed from the organisation I mentioned before, Barefoot Computing. They were the same ones that had that poster that I've been kind of borrowing from, and they have other similar activities to this. So lots of things that are kind of, unplugged paper activities you can do with children. I'm just mentioning it again because I think it's a really helpful resource, so it's worth having a little look at. Okay, so now that we've had a go at one type of algorithm, we're going to try making another one. And again, it might be good if you guys work in a pair again, if that's all right. Each of you in your pair is going to have a bit of a think about whether you know how to create anything with origami. Do you know how to fold paper to make a shape of some kind, to make a design? And you're going to work together to fold the paper and make that design. And then you're going to write the instructions for how you did it. And then after you've finished, everybody is going to swap their instructions, but not the model. So you won't know. So in your instructions, don't write down what you're trying to make. All you're going to write down is the instructions for how to make it. And then at the end, we will compare and see whether people got the same thing. And I've got some paper here if people would like some paper for your origami. Okay, we'll stop there. So don't worry if you haven't quite finished, but we'll just use what you've got so far. Can you swap your instructions? So keep your model, but swap your instructions with another group. Maybe if you two pairs swap, and if you two pairs swap. And then have a go at building somebody else's instructions. Finally. Did you do the same? Or was that your one from before? Oh, right, okay. Okay, I'll stop you there. As you can tell, we could probably spend pretty much all day on this. When you were doing that, do you think that it was more difficult to write the instructions or to follow the instructions? To follow them? Maybe? Do you guys agree? Did you find it easier to follow the instructions, or is that what it is? Yeah, everybody, by the way, just hold up the model that you've made and take a little look around the room and see whether it matches up with what you wrote. Do we have any that match? That's pretty close, isn't it? Pretty close. Well done. Okay, so it looks like something, but I don't know. I don't know what. So this kind of, I'm very impressed that people did manage to do such a good job in a short time, because really the whole point of this activity is actually, it's really hard. It's very difficult, especially if you're not using pictures. I know some people illustrated theirs a little bit with pictures, and normally, if you were learning how to do origami, you'd probably learn from a book where there were photos of every stage of the process. It wouldn't just be words. It's very difficult to communicate this kind of specific movement of different bits of paper without having an illustration. Did you want to say something?
Yeah, it's the same for Lego. That's why they use illustration.
Exactly, yeah. Lego or IKEA furniture as well, yeah. Yeah, like an instruction, it's the same thing. And it even has, with Lego, it even has the little diagram that shows you exactly how big things are so that you can check. And it removes any ambiguity. But with these instructions, there was quite a lot of ambiguity. And even if you followed it perfectly, and even if you got to the same intended point, you probably had to make a bit of a guess at some point. You probably had to think, ooh, what do they mean? They probably mean this, rather than knowing 100% certain, like, this is definitely what the instructions say. And basically, language is a difficult way to communicate this kind of process. And the process that we're following here is an algorithm. It's a precise set of instructions designed to produce a very specific outcome. And we do the same thing with computing. And really, this is the reason that programming languages exist. Programming languages allow us to eliminate some of the ambiguity that we have when we write things in normal languages. They also they allow us to kind of codify instructions and meaning.
And you made there and in us, and we can make the students engaged and creative.
Exactly, yeah, and because they can design whatever they want, and then they've got to create the instructions to go with it. Did you want to say something as well?
So you would like to add, without images, it's all about abstraction.
Absolutely, yeah.
That's why I like really best because you without images.
Yes. Yeah. Your picture. Yeah. Exactly. It's those difficult to answer questions. That's where the learning is happening, really, because it's making children realise actually a lot of what we say is ambiguous. How could I, in writing my instructions, how could I make it so that there isn't? And also, like you say, visualising that process. What could this mean? It raises a lot of questions. So what we've been doing is it's in many ways it's very technical, and it is quite similar to programming, but we don't need to use computers to do it. I've got one more activity that's in the same vein that I want to show you. Now I've suggested gathering up coins. Basically, the idea is that you have 3 of one coin and 3 of another. However, if you haven't got coins, I've got these little pieces of blue and yellow paper. So if you take 3 pieces of blue and 3 pieces of yellow, you can do the same thing. And again, if you work with a partner, then that would be great, because I think this is something it definitely helps to work as a team. So I'll just hand out the paper, and then I'll explain what the challenge is. You only need 3, actually. Stick together a bit so I don't know sorry? Oh yeah, if you, I've brought the paper so that you don't really need the points, but you could do this with counters or coins. Okay, so once you've got your counters or your coins, if you just make, again on a piece of paper, and if you haven't got paper, then I can come and bring you some, just draw like a grid of 7 squares that would fit your counters inside them. And you're going to start off with your yellow counters, or one type of coin on the left-hand side, and the other on the right-hand side. The challenge is, so here are the rules to the challenge. Each of your counters can move 1 square at a time, unless it's hopping over another counter into an empty square. But it can only hop over 1 counter, it can't hop over 2. And the coins or counters can't move backwards, so once they go forward, they can't come back. And the job is to see if you can get your counters from one side to this side, and then the counters from the other side to swap, basically. That's the aim of the puzzle. Does anyone need any more paper?
It's very carefully estimated. It's quite hard to do 7 squares. This is really neat. So I guess the challenge is to do it in the minimum number of steps. Yeah, but if so it's moves in a but I think you're thinking on the right track.
Okay, I'm going to pause you there, and don't worry because I'm not stopping you. You will have more time. It worked. Did you do it? I was going to say that'd be amazing. This takes a long time to figure out. I wouldn't expect anybody to have figured this out quite yet, unless you've seen it before, or you're just a genius. In which case, well done you. But this is it's an old puzzle and it's a hard puzzle, and the way that I have presented this puzzle to you makes it quite difficult to solve. Because I haven't really given you much of a hint about what could be some good computational thinking strategies to help us with this problem. It's actually, once you start doing it, you realise it is quite confusing and quite complicated. It seems simple, but actually there's a lot of things to think. Sorry? Recursive. Well, we'll see. So if I show you, instead of showing you this with 3 coins on one side and 3 on the other, what if I show you a slightly smaller, slightly simpler version of exactly the same puzzle? So this time, you can put one of your counters of each colour to one side, and you're going to use 5 squares instead of 7. See if it makes it any easier to try it with just 2 each of each colour. And also, this time, instead of just testing it and then saying, no, it hasn't worked, and then giving up, and then testing it and saying, no, it hasn't worked, this time, can you make a note of each of your moves? So write down what you've done, and so that then you can remember. And then if something goes a little bit wrong, you can say, okay, that didn't work, we won't do that next time, and then try a different approach. Okay, so making a note of what you've done, trying a simpler puzzle.
Okay. This is too much.
It's developing the skills that you use in coding without doing coding, and then actually making the we have some here, so if you have yours, then yeah. So you'll bring them if they have Canva, and you can so I'm going to show you this online tool. I've mentioned Scratch. Scratch is like, it's a program. It's very visual, so you don't, it's not text-based, so you don't just type it it's a is that the thing that oh, yeah, you put arrows on that's good. What else could you do? So, what, and also, like, what, yeah, so how about that? So do you think you can remember that and write down what you did? And when you write it down, what you need to do is like B, Y, like which colour you want. Or maybe you can try that. See if you can do it. See, oh, and you've got help with move symbols as well. Do you know what will help? It will help if you make a note of the colours of the characters as well as the position. Yeah, so maybe put it like, just because it's easy to see the pattern if you know colours.
We have names.
Yeah, you made an array. If you want to, if it helps you. I was just saying to those guys, I find the easiest way to name them is just by colour. And that's, I know this is more common, it's a lot more precise. So then if you were doing computer science at a higher level, that's how you do it. But for kind of solving the problem, you don't need that much information. You can do it just by knowing that this one's yellow, I'm moving the yellow one, I'm moving the blue one, I'm moving the yellow one. That will. Oh yeah, okay. Oh yeah. Sorry, I'm not reading properly. Yeah, so B, Y.
So yeah, you took one step to the right.
B, Y, Y, B. That's the thing that's the pattern.
Okay.
And that will help you. So without even worrying about the numbers and the jumps and steps, B, Y, Y.
I remember that.
Okay, so again, if you haven't quite finished, don't worry. Don't worry. We're gonna have a go at reapplying it to the longer one in a second. So how did you get on with the simpler puzzle? Did you manage it? Yeah? Can anybody describe what your pattern was like? How did you, maybe in fact, if I'm gonna take this out of presentation mode, can you get me to do it now? So what do I need to do first? Ah, well done. Good. Yeah? So if you guys just did it, then see if you can instruct, can you remember what you did, do you think? See if you can instruct me to do it, and I'll just do it on the screen. So what shall I move first? You can call them A and B if you want. As in, sorry, these two can be A's, and these two can be B's. So A. B jump. That's so did anyone else find this is the first point where basically if you move this here, you get stuck. Did you notice that? Yeah, no, that's fine. So it's this last one. So just to recap, I've gone A and then I've gone B, and now I'm going to do another B. Yeah. Then what? A, and then B, and then B, and then A. And obviously there are lots of different ways that you could write down that algorithm, and I've seen that each of you has developed your own kind of language for describing it. Your own coding language, which is really interesting. And it's interesting to know which information people chose to write down. So some people were writing the position that you started in and the position you finished in. Some people were talking about the color or the starting position of the coin. Some people named each one individually, and also talking about whether it's jumping or whether it's moving as well. But I'm going to say this problem is easiest to solve if you break it down to you just take the minimum amount of information. And the minimum amount of information is just which of the coins you're moving at any given time. So for this, for if you're using A and B, the way that I just did it, I moved A, and I did that once. So I moved one A coin, and then I moved two B coins, and then I moved two A coins, two B coins, and then one A again. So I've got kind of, there's a few things we could look at if we're thinking about this as being a pattern. One of the things is that we kind of alternate between the coins that we're moving. So here I'm moving A, B, A, B, A. But also looking at what happens to this number, it gets bigger and then it gets smaller. And the number that's in the middle happens 3 times, 2, 2, 2. And it is also the number of coins that there are. So if we could translate this pattern and we could try and think about how you might scale this pattern up for a larger problem, what do you think it might look like? What do you think would be different, and what do you think could be the same? Yeah?
A, B, C.
So how many A's and how many? Sorry?
3 coins in 6 coins.
Yeah, but you're still going to have 3 A's and 3 B's. So, yeah, you don't need any C's. So you'll just be like A, but then you might have 3 B's at some point, if that makes sense, instead of just 2 B's. Okay, so I'll leave this with you. I'll give you another minute or two to have a little go and see if you can get the 3 coins working. And then, yeah, and then after that, it's up to you. I can tell you the answer if you want, or you can continue to work on it afterwards.
Have you got it? Which one? The three ones?
Yeah.
No, not yet. You want me to have it as a trial or working with this algorithm?
So starting with this algorithm, see if you can adapt this algorithm to work with.
Okay, I'm going to have a go at doing it on the screen. So again, if you can give me the instructions based on what you've written down. So should I start with A or B? Should I start with A or B? Yeah, A. How many? 1. Yeah, so we always start with 1. Yeah, and then B. How many? B1. So if I do B and then I go back to A, which one has to move? This one here? So if I move this one here, and then what happens next? So I've gone A, B, A, and then which one am I moving now? This one? This one? This one? Ah. Now here, by moving this, yeah, so can you see what has happened now? The moment that I move a coin, and then I move it, and I put it next to the same type of coin, I block myself. I can't go any further. So the only time that I will put a coin so that it finishes, so that it's next to the same type of coin, is when I'm finishing, when I'm ending it, and I'm putting it in its final position. So that one has to come back, and I think that one has to come back too. So I've done A and then B. So I now know that if I move A again, I get stuck. So I'm going to have to move another B. So we've got A, B, B. Then what? This one? So A, and then another A, and then another A. So I've got 1A, 2B, 3A. Then what? This one? So B, how many? B, B. Well, the only other thing I could do is move this, and that doesn't help me. So it must be another B. And then we're back on A's. How many? 1, 2, 3. So that's 1A, 2B, 3A, 3B, and then 3A, 2B, and then finally 1A. So it's quite hard to remember. And again, it's confusing. There's a lot of information to hold in your head in one go. I've made a note of the way that this works with a few different numbers of coins. And when you look at the patterns, I think it makes it a little bit easier, to see what's going on. Just get rid of that. So I'm going to put it big, so just wait a second. Coincide. There we go. Yeah, so I think it makes it a little bit easier to see what's going on. The thing that you notice is, the top one is for 2 of each coin, that's for 3 of each coin, that's for 4 of each coin, and that's for 5 of each coin. And if you look, you'll see that when it's 5 of each coin, there are 3 5s. When there's 4 of each coin, there's 3 4s. When there's 3, there's 3 3s. And when there's 2, there's 3 2s. It's quite hard to say. And the other numbers get bigger, and then they get smaller again. It's almost a little bit like a normal distribution curve, but with a flat bit in the middle. I suppose it would be it's kind of like that. So this is not a simple algorithm. It's quite a difficult algorithm to explain. And the other thing that I think we've found quite difficult about it is that I described algorithms as sometimes being a set of instructions, like a list of instructions, and sometimes they are. But this algorithm, it works better if you think more of it as a set of rules. So you're thinking about things like you say, okay, never move a coin next to the same type of coin unless it's at the final position. That's a rule, and if you follow that rule, you will be able to complete this puzzle more easily. And writing down rules like that is sometimes more helpful than trying to write down the actual sequence, the order of the instructions. So this is a kind of another version of what an algorithm could be. As I said before, this is another unplugged algorithm activity, but it's something that you might do with older children, so compared with the previous activities that we've looked at. Another one of those words that we mentioned before, decomposition, is this idea of breaking a problem down into smaller solvable parts. And to illustrate this, I have got a program so this is the output of a program that I've made in a piece of software called Snap. You can do exactly the same thing with Scratch. So any of you that are familiar with Scratch, you could do the same thing. The reason that I did it in Snap was because I wasn't sure whether we'd have the laptops, and Snap works on iPads. But you could do it in either. It would be very, very similar. Snap is a programming language where you can give your character, and in this case, my character is this arrow. I can give it instructions. I can tell it to move around, and as it moves around, I can make it draw. So looking at this puzzle, if I've given this character the instructions that it needed to move along all of these lines and make all of these shapes, how do you think I did that? Or how would you go about solving this problem yourself? How could you decompose this problem into smaller parts to make it easier to solve?
Just give the instruction for just one, and give the same instruction for the number of.
Yeah, so it's meant to. So if I can figure out how to make one house, then I can just repeat that process and I can make lots of houses. But is that as far as I can take this? Is that the smallest way that I can split this up? What else could I try and do? So now that I'm looking at just this one house, how would you make a house? You could just do it. You could go across down. You could just do each line individually and program it like that. But if you're thinking about what your program might look like, to make this part of the house, it's going to go across and then turn. It's going to go thinking like a B-bot. If we were a B-bot here, we'd be going forward, right, forward, right, forward, right, forward, right. So to make this shape, we can use repetition, and repetition makes programming more efficient and easier. So if you can find a pattern in the shape that's going to allow you to repeat an instruction, that is going to save you a little bit of time. So what I would do is, once I had broken it down into a single house, I might then think about that house in terms of the house itself, the square at the bottom, and the roof on top, so the kind of triangular part and the square part. You might program a whole triangle, or you might just program those two lines. That's kind of up to you. And the nice thing about this puzzle is that people tend to choose lots of different strategies for solving the problem. I'm going to show you one strategy, but actually you end up finding that there are loads of different answers, and also people make little mistakes along the way that teach them a lot of things about maths. So I'm kind of creating a situation where you can make a helpful mistake. Because the thing about computing and computational thinking, and this is something that I think we struggle a lot with in the English education system, because there's a huge amount of testing that goes on. There's a huge amount of emphasis placed on children getting things right and not making mistakes. And that makes it really difficult to teach them to have an attitude where they're confident enough to take risks in computing. And actually, computing is a subject where you really need to be comfortable with taking risks and with making mistakes, because your mistakes are where your learning happens. When you try something and it doesn't work, there's probably a really good lesson that you can take from that you can then apply to your next activity. And so I'll show you an example of that in a minute. But this is an example of what a Snap script might look like. In Snap, you name your instructions by what they do. So this bit at the top, I've written draw square. I've named my instruction to define what my script does. And then I've put the blocks together. So in Snap, your character has a kind of invisible pen. And if you tell it to put that pen down, then it will start leaving a line behind it when it moves. So that's why my first instruction is pen down. After that, I've got a repeat loop, and it says repeat 4. Inside the repeat loop, it's going to move 50 steps, and so that might seem like a lot. And obviously, so just like with the B-bots, I often start by acting this out. Obviously, if I acted that out, I would be off in the other room. So I'm not going to move 50 steps in real life, but I usually get the children to instruct me to do this first. So I'll say, okay, I'll put my pen down, I'll move maybe 2 steps in real life, and then I'll turn. and then they need to think about which direction I'm turning in and how much I'm turning in. So they're applying their mathematical knowledge of angles and right angles to make it turn 90 degrees, and then they go forward again. And obviously, while they're instructing me step by step, they notice that there's a pattern, there's some repetition happening with their instructions. And that's what makes sense of that idea of the repeat loop. So now that you've seen the instructions that make a square, how would you adapt that? How would you change those instructions if you wanted to make a triangle instead?
I prefer to use like over 2 x and y axis in Scratch.
Yeah, you could do that. Yeah, so that's true. So yeah, and then you can design exactly where they go, and you just need to think about what order. Yeah, you could do that. Did you want to say something else? So you would change the repeat number to 3, and then this one to 45. Okay, interesting. Anyone have any other suggestions? Okay, I'm going to test it out. So I will open up, I'll open up Snap. And Snap is made by Berkeley University. So if you search for Berkeley Snap, you get this website. Build your own blocks, and then you can go to Run Snap Now. As I said, you could use Scratch to do exactly the same thing, and I really like Scratch. I think it's great, so I would also recommend that. Scratch is made by MIT University, and their website looks like this. If you click Create, then you can do things that way. But to keep it the same as the presentation, I'm going to use Snap. So it looks like this, and I will start off with my square. So I had 50 steps. I had turning 90. I had a pen down block. And I had a repeat loop, which was repeat 4, which is down here somewhere. And the way that those repeat loops work, basically any instruction that is inside that loop will get repeated. Anything outside it won't. It will just move on, or do them one after the other. So I think that's the same, isn't it? So let's test that out. Okay, so I've got a square, and now I'm going to have a go at making my triangle. So rather than delete my square instructions, I'm just going to right-click at the very top, and I'm going to duplicate them. And then I'm going to try number 3 in here. And you said 45. Sorry? Together. Okay. Oh, do you mean steps? Oh, okay. So what I can do is go to pen, and there's a block called clear, and that deletes the square. So now I can test out this new instruction. And that process, the process of kind of resetting your instructions and starting from scratch, excuse the pun, is called in programming, it's called initialization. It basically just means starting again. And it's a really important skill for children to learn, because it can get really confusing if they're always adding new bits to their blocks and then testing it and then adding more, and they never get things back to the way they started. So it's always important to show children how they can use the blocks like clear to rub out their line when they want to start again. And it's actually a bit off the screen, but there is a green flag at the top of the screen. When I click the green flag, it will follow this instruction, because it says when green flag clicked. I might use the block that you suggested just now to change the position, which was move to X, Y, because in the background of my stage, this white area over here, is an invisible X and Y axis. And so the 0, 0 is in the center of my screen. So now when I press my green flag, I go back to the middle and everything gets rubbed out. So there's my square. And then let's try this triangle. Now, useful mistakes, because this isn't a triangle, but if I keep going, let's see what I get. So I've got an octagon. So instead of deleting my instructions, what I'm going to do is I'm going to change my repeat number to the number 8. And now I've made a new set of instructions which should, when I click on it, draw an entire octagon. So now we've discovered how to do something new. And I'm even going to make a new block. And I'm going to go to the pen section. Down at the bottom, it says make a block. And I'm going to call it octagon. So any ideas why 45 gives us an octagon? What is it about 45? So it's good to go through this process because this is usually what children will do. Actually, children, usually the number that they try first when they're doing their triangle is 60. And the reason that they try 60, well, does anyone think they can guess why they choose 60? If you know that a square, if you know that a square is 90 degrees, you might think, based on your knowledge of angles and squares, you might think, okay, well, the interior angles of a square are 90 degrees. So if I'm trying to make a triangle, then I need to think about the interior angles of a triangle. And they add up to 180 degrees. So if it's got, so that whole logical process, that step-by-step process of thinking through and getting to the point where you try number 60, is actually using really good computational thinking skills. And it's applying mathematical knowledge to a different context. In this particular case, though, 60 doesn't give you a triangle either. Any ideas what 60 might give you? 60 will give you a hexagon. Yeah. I'll just demonstrate that to prove it. Oop, that's wrong, isn't it? 60. There you go. So I'm going to click the green flag to start again, and then try my hexagon. So there we go. That gives us a hexagon. So the reason for that is that the reason that 90 degrees creates a square is not the interior, because it's the interior angle of a square. That's the misconception. It's actually because it's the exterior angle of the square. The outside angle of the square, that's how you're turning. If you think about where your character is moving, they're pointing out of the square, and then they need to get back, so they're pointing along the square. So it's that outer angle that's important. Which means if you want to figure out how to make a triangle, there's a few ways you could work it out. One of them is by thinking, if it's the exterior angle, and I know that the interior angle is 60, the exterior angle is a straight line minus 60. So it's going to be 120. There is another way that you can work it out, which is possibly a little bit easier, and that is by thinking about the total number of degrees that you turn whenever you make a shape. So if I make a square, I go all the way around because I'm making a whole square. If I make a hexagon, I go all the way around because I'm making a hexagon. Whatever the shape is, I'm going to turn all the way around and get back to the start. So for every single shape, the total number of degrees is 360. And that's why when we make a square, we turn 90 degrees 4 times. 90 degrees times 4 is 360. To make a hexagon, we turn 60 degrees 6 times. 6 times 60 is 360. And so when you write down these numbers and you notice these pairs of numbers, you start to see that pattern. And when you see children make this realization where they're like, oh, it's a really, really glorious moment. And it becomes so much more satisfying for them because they can make the whole thing happen in one go. However, I'm going to try my triangle one now. I'm going to click on this block, which I will add to my initialization script, which is called point in direction. And it resets it so that it's pointing back. No problem. So it's pointing back the way as it started. And then you'll see that if I try my square instruction, which is in the pen section, isn't it? So I'm going to click on square. I've got my square. Now I'm going to try my triangle. But unfortunately, it doesn't look much like a house. It looks a bit more like an envelope. And that is, well, why? Why is that? What could I do to change it? So again, this is a helpful mistake. I need to think about how I could flip that triangle around. What could I do in my program that would make it appear the other way? Again, there are loads of solutions to this problem, and that's why I like it. So go to... Before drawing the triangle. Do you know what I'm going to do? I'm going to name my triangle block so that it's easier for me to see what's going on. I'm also going to make my window a little bit smaller, I think. So I've gone to make a block, and then I'm just dragging my code in. And then, can I make this smaller? Here we go. There we go. So now, if I go square and triangle, and you want me to add in something in between? You want me to add in 0, 0?
I think it's a bad idea. Let's give it a try.
Okay. So if you think about it, when you make a square, you start at point 0 because the green flag takes us to 0, 0. And then when you make your square, you do a full turn all the way around. So you actually end up in that position already, which is why you can't see any effect when you follow that instruction. But you could certainly do something to do with adding an instruction in between. It's not so much the position that matters as the direction that it's facing in. So you could add another turn. And so let's do it one bit at a time. So if he's made his square, how could he turn so that he's pointing in the right direction now to make a triangle? 45 degrees clockwise or anti-clockwise? Anti-clockwise? Okay, and 45? Okay, let's try. Well, let's have a look. Okay, we're on the right track, 45 isn't quite enough. 120? Not 120? Okay, so now we're trying to get from here to here. Thinking back to what we said about triangles earlier, this time, it's not the exterior angle, it is the interior angle. So this time, it is going to be 60, as you say, because he's going to reposition and back up like that. So let's try that out. Okay. And now it's sort of facing at a funny angle, so I could also add on, I could get it to turn back 60 degrees afterwards as well, if I wanted to. Oh, probably use my initialization script. There we go. Lovely. So yeah, that's one solution. It's not the only solution though. Any other ideas?
Yes, I prefer to remove repeat from the triangle block.
Mm-hmm.
And do it step by step.
So instead of trying to make a triangle, just do one line at a time.
45. Then pen down.
Maybe you could make a block called roof, and that gets it to turn back 60. And then do the root, like do one side of the triangle with a move block, turn, and then do the other side of the triangle so that it gets back to the end. Is another way that you could do it. Yeah, that's one way. Yeah, another way that you can do it is just by changing the direction of the triangle, because if the square is clockwise, and then the triangle starts at the same point, if the triangle goes anti-clockwise, then it comes back and then it finishes in the same position. So I can edit my triangle script, which I do down here. And there's two ways that you can reverse the direction. You can either use the other block, because at the moment I've got the clockwise block, or you can cheat a little bit and you can actually just put a minus number inside instead. And that will work exactly the same. So hopefully now, there we go. I could do it that way as well. The only thing here is that now I finish on the left-hand side of my sprite. And if I want to repeat the instruction, then I'm going to be in the wrong place. So maybe at this point, I might need to, before I put my repeat, I'm going to need to use another motion block. And I'm going to need to move along the length of the shape. And then once I've done that, I can add those into my repeat, and then I can give it a try. Okay, so this, as I said, this is a problem that has lots of different solutions, and there are loads and loads of ways of doing it. And I think that that's probably true of all the best coding activities, really, because it enables children to be creative. Even with problem solving, even with maths, you're still having to kind of apply your imagination, think in an abstract way, like you said, in kind of to solve the same problem in lots of different ways. I'm going to leave you with a few little bits of activities activity that you might want to have a very quick go at now because we've only got 5 minutes left, or you might want to just take them with you. And because you can use this software from any computer that's connected to the internet. What I've got is a selection of scripts which I've created in Snap. And each of those scripts makes a different pattern in very much the same way that we've just been doing. And the patterns are all on the sheet, but I've mixed the patterns up so that they're in the wrong order. When I show this to children, what I get them to do, and this is a kind of a process of looking for patterns and about abstraction, thinking ahead, imagining what might happen, and applying mathematical knowledge. Before they go near a computer, I say to them, look at these scripts, read them through, and talk to the person next to you. Which do you think matches with which, and why? And so they're really thinking about it before they do it. Then, when they've made their prediction, and only then, do they go onto the computer, they give it a go themselves, and they find out whether their prediction was correct. So, as I say, I will leave these with you. It's up to you if you would like to try them out now, or if you would like to just take them and maybe try them again in the future. Okay, just while you're looking at that, and this is basically just because I can't be in a room with teachers without recommending this this particular resource, because I think it's really, really helpful. So there's two things I want to mention. First thing is, programming in English primary schools has been challenging, obviously, for teachers. And we find that when teachers who are not that confident start using programming activities, all of the activities that they do tend to be on either end of this spectrum. So basically, we find lots of teachers that do activities where the children just copy the instructions and they don't do anything creative themselves, they don't experiment, they don't try things out, they just have to follow what the teacher does. Because the teachers are a bit scared that if the kids can go do whatever they like, then the teacher won't be able to answer their questions. The other end of the spectrum is when teachers think, well, I don't really know about this, so you guys, why don't you just try it out for yourself, just mess around and see what happens. And a lot of people do that too. I think sometimes that can be quite beneficial. Sometimes children make interesting discoveries. But I think it's more helpful when you can structure that a little bit. You can do activities like guided exploration activities, for example, which are more about kind of setting a few constraints, saying to children, here are 3 different instruction blocks. Can you find out what they do? Can you put them together in interesting ways? Can you change the numbers and see what happens? So sometimes by slightly limiting what the options are, you're enabling them to make more useful discoveries in their learning. So it's just good to think about programming activities in those terms. And then the final thing that I want to say is just look at Scratch Maths. It's a research project by UCL, University College London, and there's a whole set of 2 years worth of programming and maths resources. They're really detailed and really helpful, and they talk about all the different ways that you can link teaching programming to different areas of the curriculum. So there's, I think the first module is about, a little bit like what we just did, kind of making geometric patterns. And because of the mathematics and the symmetry, there's a lot in there about the links with Islamic art, but also with patterns in nature, so thinking about things like snowflakes and that sort of thing. And there's loads of stuff. It's really mathsy, but it's a really kind of practical way of visualizing maths and really developing a deeper understanding of more abstract ideas. So I really hope that some of that has been helpful. As I said, I've got a few more sheets. If anybody wants to grab some, you are more than welcome to. But otherwise, thank you very much, and I hope that you enjoy the last session. Very welcome.